In this presentation, we'll look at the zeros of transfer functions and how they depend upon where the input and output location are. And to start us off, we'll look at the frequency response of the double mode beam system. We introduced this system before and analyzed its dynamics. Let's recall the situation. We have an input force F acting on the left side of the beam. The beam is supported by two springs, and the output Y is taken at a distance epsilon L from the left end. The length of the beam is L, and the mass is M. We found before that the beam had two modes. One mode was the bounce mode, where the beam moves up and down without tilting. The poles of this mode are plus and minus j square root of 2k over m. The other mode is the tilt mode. It's where the beam rotates about its center of mass. And its poles are plus and minus j square root of 6k over m. We found the transfer function for this system before, and found it in terms of the poles and the zeros of the system. And we saw that the poles were independent of where the output was located, but the zeros depended upon the output location. The zeros were plus and minus j square root of 2k over m times square root of epsilon over epsilon minus 1/3, where epsilon told how far the output location was down the beam. If we plot this function, the function that shows where the zeros are, versus epsilon, we get the following graph. This graph shows the zeros of the transfer function as a function of epsilon. And what you see is as epsilon increases from 1/3, the zeros are decreasing in frequency. When epsilon equals 1, that is, the output location is on the far right side of the beam, the zeros are at plus and minus j square root of 3k over m. Note that when epsilon equals 1/2, the frequency of the zeros is the same as the frequency of the tilt mode, square root of 6k over m. For epsilon between 1/3 and 1/2, the frequency of the zeros is greater than the frequency of the tilt mode. And for epsilon between 1/2 and 1, the frequency of the zeros is between that of the tilt mode and that of the bounce mode. Here these results are shown in the S-plane for the various values of epsilon we're considering. Denote the frequency of the bounce mode, square root of 2k over m, as omega 1, and denote the frequency of the tilt mode, square root of 6k over m, as omega 2. We'll denote the zeros by omega sub 0, and we'll plot the poles and zeros on the imaginary axis. For epsilon between 1/3 and 1/2, we have the arrangement of poles and zeros shown in the left figure. You'll notice the frequency of the poles is less than the frequency of the zero. For epsilon equals 1/2, we have the situation shown on the right in the figure. The frequency of the zero is the same as the frequency of the tilt mode, and so you see the zero drawn right on top of the tilt mode poles. Let's now examine the case where epsilon is between 1/2 and 1. In this case, the frequency of the zeros is between that of the bounce mode and the tilt mode, as you see here, with the zeros lying between the poles at omega 1 and omega 2. This situation is referred to as pole zero interlacing, and it's an important property in the control of flexible mechanical systems. Let's now look at the frequency responses for these three cases. the case where epsilon is between 1/3 and 1/2, the case where epsilon equals 1/2, and the case where epsilon is between 1/2 and 1. The shape of the frequency response will be different in each one of these cases, and it's different because of the placement of the zeros. Whether the zeros are a higher frequency than the tilt mode, whether they're the same frequency as the tilt mode, or whether they're between the tilt mode and the bounce mode. Let's look at each of these in detail. Here's a sketch of the frequency response for the case where the output is on the left end of the beam. That is, epsilon is between 1/3 and 1/2. And what you'll note is the frequency of the zero, omega 0, where the output is completely blocked, is at a frequency higher than the tilt mode and the bounce mode, which you see as omega 1 and omega 2 on this frequency response plot. The second case is when epsilon equals 1/2, and then the frequency of the zeros is the same as the frequency of the tilt mode poles, square root of 6k over m. In this case, you cannot see the resonance from the poles, the tilt mode poles, in the frequency response plot, so the tilt mode is unobservable. The frequency response from the input F to the output at the center of the beam doesn't show the tilt mode at all. The last case is where the sensor is measuring the vibration at the right end of the beam. So epsilon is between 1/2 and 1. And in this case, the frequency of the zeros is between that of the bounce mode, omega 1, and the tilt mode, omega 2. In this case, the frequency response plot looks as shown here, and you can see the pair of imaginary zeros blocking the response at the frequency omega 0. That frequency between the resonances at omega 1 and omega 2. So let's recap what we've seen. We've seen that the frequencies of the pair of zeros on the imaginary axis depends upon where the sensor is placed, exactly where on the beam we are measuring the displacement of. If the sensor is toward the left end of the beam, then the frequency of these zeros is above that of both the bounce mode and the tilt mode. So if the force input at the left end of the beam was at high frequency, a frequency higher than the bounce mode and the tilt mode, the only places along the beam where there would be no vibration in response to this input would be locations between 1/3 and 1/2 down the beam from the left end. If the sensor was placed at the center of the beam, then the tilt mode would be unobservable. Let us suppose that the frequency of the excitation at the left end of the beam was between square root of 3k over m and square root of 6k over m. Then there would be a location between the middle of the beam and the far right end of the beam where there would be no response to this input. That is indicated by the fact that there would be a pair of zeros on the imaginary axis between the poles of the bounce mode and the tilt mode. Let's look again at the unobservability of the tilt mode when epsilon equals 1/2. And to do this, we'll just substitute in epsilon equals 1/2 into the transfer function that we found before. We had a general form of the system transfer function that we found in an earlier lecture. And when we substitute epsilon equals 1/2 into this, the transfer function simplifies as follows. The numerator will be is squared plus 1/2 kl squared. And the denominator will be ms squared plus 2k times is squared plus 1/2 kl squared. And you'll notice the same term in the numerator and the denominator. These terms will cancel out. That's pole zero cancellation. That is what's making the tilt mode unobservable. And so the transfer function then becomes 1 over ms squared plus 2k. That is, we just see the bounce mode. Let's remind ourselves how the frequency of the zeros changes with epsilon. We had an equation for that. It was omega 0 equals square root of 2k over m times square root of epsilon divided by epsilon minus 1/3. And if we take epsilon equal to 1, we obtain the smallest value of this quantity. That minimum value of omega 0 is square root of 3k over m. What this means is that for any frequency omega 0 star greater than square root of 3k over m, there will be an epsilon such that omega 0 star is equal to this value. What that means is for any such frequency omega 0 star that we specify, we can find a location on the beam such that the frequency of the zeros is equal to omega 0 star. Here's how I want you to think about this. If I were to give you a value of omega 0 star, a target value, say, for the zeros of the system, you could then find a place on the beam, label it epsilon star, such that the transfer function between the input force F and the output at that location had a pair of zeros at plus and minus j omega 0 star. So the transfer function between the input F and the output y at epsilon star times L away from the left end of the beam would have a pair of zeros at plus and minus j omega star. So we'd see that the frequency response plot would look like this, with omega 0 star being the specified value. You'll note in this frequency response that at the frequency omega 0 star, the transfer function has zero gain. So that means the input is completely blocked on its way to the output. The input is sinusoidal, but the output doesn't show the sinusoid at the frequency omega 0 star. So for any frequency omega 0 star greater than square root of 3k over m, we can put in a harmonic input, f of t equals sine omega 0 star t, into our system, and in response get an output y of t is equal to 0. There's a location along the beam between epsilon equals 1/3 and epsilon equals 1 such that the beam does not respond to the sinusoidal input at this frequency. Now the location where this is depends upon the frequency of the input. Here's what's happening physically in this case. The beam is rotating and bouncing in such a way that one location upon the beam at epsilon star L is not moving. So it's as if the beam is rotating about this point. A sensor at this point measures zero displacement in response to the force acting at the left end of the beam. Now what I'd like to discuss is how this point, the point of no movement, changes as the frequency changes. So if we start off with a low frequency, omega 0 star equals square root of 3k over m, then this point of no rotation will be at the far right end of the beam. And as the frequency is increased from this value, the point of no motion moves toward the left. As omega 0 star approaches infinity, this point approaches 1/3 the way down the beam from the left end. So this is the key thing I want you to consider as we're about to look at a video clip of a vibration problem, that the point of 0 vibration will move along the structure as the frequency of the input is increased. So here is the experiment. We have a structure consisting of 3 masses and some stiffness elements mounted on top of a platform that is vibrating. And as the frequency is changing from low frequency to high frequency, you can notice different locations where there is no vibration on the structure. This point of no vibration moves along the structure, as we can see here. As the frequency is increased, the point of no vibration is moving up the structure. If you pay careful attention, you can see this as the frequency is increased. Here the point of no vibration is at the central mass. Here the point of no vibration is halfway between the top mass and the central mass. In our next lecture, we'll continue to examine the impact that the output location has upon the transfer function.